Hi, I am Mrityunjay. Today I will explain my project Local LLM Instrumentation Tracing and Replay Platform, which is a lightweight terminal UI that hooks into llama.cpp to give you a real-time visibility into what's happening inside a transformer model during inference. Firstly, let's understand what is inference. Inference can be understood as the model actually generating a response to your prompt as different from training when it actually learned from the data. It's not like when we download a model, we can just run it as an executable file. Instead, we get a list of artifacts, and using those artifacts, we make inferences. With it, using an inference engine like llama.cpp or VLLM and so on. Let's see the part of transformers important to this project. First up, we have tokenization. Tokenization involves breaking down text into smaller units known as tokens, which the model can process and understand. These tokens are based on model's vocabulary, such as, for example, let's take the text of "the dog sat on the couch." Initially, we standardize the text, meaning we'll turn all the letters into lowercase letters, remove the commas, etc. Next, we tokenize it, meaning we convert the standardized text into tokens. For example, here we have converted it into tokens of the, dog, sat, etc. And based on model's vocabulary, we index them into different token indexes. And to make sure model understands this, we convert them into vector encodings of indexes. Next, we have layers of transformers. A layer is one step of processing inside the model. The transformer has many layers stacked on top of each other, and the text passes through them one by one. Each layer refines the model's understanding a little more before passing it to the next layer. Next is attention matrix. For decoder only model, attention matrix is score that tells us how much relevant each earlier token is to the current token. For example, the token of do and token of nothing is very much relevant to one another based on opacity, and the token of mother and token of nothing are not a lot relevant to one another. Let's understand what happens inside a transformer. Transformer takes the input prompt and tokenizes it into different tokens. As you can see here, it takes the input prompt of the cat sat on the, and it tokenizes it into different tokens such as the cat sat on the, and using those tokens, it creates token embeddings, which is a vector that represents that tokens, meaning in a way model can do math with, and positional encoding, so model can understand the order of tokens. The combined embeddings are passed through the model's stack of layers. In each layer, there is self-attention that lets each token look back at its previous tokens, and feed-forward network, which further refines each token's representation. This process is repeated multiple times. After the final layer, model predicts the probability of the next probable token. After model picks a token and adds it to the sequence, and entire process is repeated until the response is completed. The problem statement requires me to see inside a running LLM in real time from the terminal without touching the model's code. It requires me to capture real-time states as tokens flow through the architecture and present that data in an interactive TUI. Let's see the demo of what I have built. Here I am running PHI-3 Mini locally, which is a small language model with 3.8 billion parameters. Here I have given the prompt to write a for loop in Python. As the model generates tokens, the tool is hooking onto every layer of the transformer. On the left in panel 1, every shown token is model generated. Here that prints all are the token. Each layer expands into a 32 layer capture because PHI-3 has 32 transformer layers. Pressing enter expands into that token's layer. Here I can see the latency for each of the 32 layers. Panel 3 shows runtime metrics, whichever layer is selected, and the tensor shape, exact latency and sparsity percentage. Panel 4 is the real attention matrix. As you can see, it is a causal masking pattern. Each token only attends to itself and its previous token, which is exactly how a decoder only model should behave. Once inference is completed, panel 5 computes an anomaly report. It averages latency and sparsity across all the tokens per layer and flags any layer that's significantly slower or sparser than the mean. Let me explain the implementation details. This is a local single process tool that talks directly to llama.cpp's C API. So instead of API endpoints, the key integration point is a callback function. llama.cpp exposes a hook called cbeval. It fires after every single tensor operation. Inside the model's forward pass, I register this callback before creating the inference context. This is the entire integration. From here, every time the model computes anything, my function gets called with a pointer to that tensor. Inside that callback, I filter out two tensor responses, L_out, which is a final output of each transformer layer, and KQ softmax, which is the attention weight matrix. Everything else gets skipped. The UI itself is built with FTX UI, a CPP library for terminal interfaces. It re-renders every 0.2 seconds, reading whatever's currently in the ring buffer and the token's history structure. Let's see this demo again for a different prompt. The cat sat on the. Running on a different prompt produces different token sequence and different latency numbers each time, confirming this is live. This was local LLM instrumentation, tracing and replay platform, a lightweight terminal UI that hooks into llama.cpp to give you a real-time visibility into what's happening inside a transformer during inference. Thank you.